podcast is brought to you by LMU Munich.
Okay, so welcome everybody again to the second lecture on D-branes. Okay. So it's too loud now. Like this. Can you hear me? Can you hear me? Okay, so what I didn't tell you last time, it's the final thing on D-branes, I will tell you now, is so we had this annulus partition function. Yeah, remember? So the formula for that was that we compute this integral over this modular parameter of the annulus of the cylinder, and there's a partition function here, where this is the trace over all open string excitations, and weighted, so to say, with the eigenvalue under the zero operator, which is sort of the Hamiltonian here. Okay, so and the motivation for introducing these boundary states we had last time was that we change our view on this diagram in the sense that we exchange space and time, so that now time goes in this direction and the worldsheet space direction goes along the circle, so that we can view this diagram also as a closed string exchange between these two boundaries. And I introduced this boundary state for a description of how each closed string couples to the boundary. So this was a formal sum over states in the Hilbert space, closed string. And then we had these coefficients, alpha and j, which I determined by requiring that these boundary states satisfies some gluing conditions, which were of the form excuse me? Yeah, that's what I'm trying to do now. So, you see? Hello? Hello? Can you still hear me? Good. Okay. So we have these gluing conditions. These are called gluing conditions, plus minus, depending on whether we have a Neumann or Dirichlet boundary condition. Acting on this on the boundary state has to vanish. Yeah? And the solution I gave explicitly, I can write it again. In terms of these oscillators, it was an exponential of plus minus sum over all positive numbers, positive excitations, 1 over n alpha minus n on the vacuum. Yeah? So implicitly, we have here now determined all these coefficients alpha for all the states appearing in the closed string Hilbert space. And now we can use this, really, to compute this diagram in a different way. So what we do is we have our boundary state on the left. This emits a closed string. We propagate this closed string to the right-hand side. Now we're doing a sort of time translation if you want. And here now is the closed string Hamiltonian. And then we absorb this closed string again, on the right-hand side with the other boundary state. And the statement is that this expression is the same as the right-hand side over there. So as the open string partition function. Yeah. So this is the mathematical, so to say, situation, or the mathematical formula describing this closed string, open string duality of this particular diagram. And in the exercises this afternoon, you will really compute this overlap. Now with all the data which are on the blackboard now, and in this form, closed string Hamiltonian is known, this form, you can really show that you get a similar result. So what you will find, this is exercise, B. And eventually we also integrate, sorry, that's one mistake. We integrate over L, this new modular parameter, L. If you do this, you will find expression like, so for Neumann, you will get again the eta function with an argument 2il. And for Dirichlet now, you will get 1 over eta 2il. And now here you find, because for the Dirichlet boundary condition, you still have to integrate here over the momentum now, and you will get this extra factor here. I guess square root of 2L probably, yeah, something like that. Yeah, and you see now that this is related to the open string expression where we had this parameter t by doing a modular transformation. Yeah?
How can this possibly be to integrate over?
Yeah, okay, good. And we do it without the L. Okay. But here's the L, the integrand. It's just the integrand, yeah? Yeah. Then this is the, yeah. Closed string Hamiltonian. Okay, and so what is the relation between L and T? So L, so let's say the length of the cylinder. So we have now these two views on it. Let's draw it again. I do it correctly. So here we have in the open string channel, this is an open string. This has length pi, and this here is 2 pi times t, the length of this circle here. And in the closed string, we have a different interpretation. We call this is now the length of a closed string, which is normalized to 2 pi. And this here is the length 2 pi L. So the ratio, of course, has to be the same. So we find that 2 pi 2t, this divided by that should be that divided by that. This is the modular parameter of the annulus. So this will be 1 over L. So you find that L, is 1 over 2t. So this is the relation between the parameter in closed string, L, and the parameter in open string. You see there's a 1 over it. So in order to relate these two expressions, so what we have to do is, so we write, for instance, this result as 1 over 2 pi il. Then we use this relation. So it's I over t. And now you see that we can use now the modular property of the Dedekind eta functions. This, which I explained last time, that eta with the argument minus 1 over tau is square root of minus I tau, eta of tau, to write this as precisely as 1 over eta it square root of t. Yeah? And this is precisely the result we already computed in the open string channel. Yeah? So the closed string result, which is the overlap of two boundary states, is related to the open string result, which is just a trace over the open string excitations for such a modular transformation. Is that clear? Yeah? So this is different to the closed string. For the closed string, I think wasn't explained, but there you have a very similar story. There you have a torus. Maybe I at least explain this very shortly. So for the closed string, you would also compute such a one-loop diagram, which would be the torus diagram. Yeah. So closed string with one loop is a torus. Then you would also have sort of the expression for the cosmological constant at one loop, which has a different measure now. And now the modular parameter of a torus, is complex. Here was real. It's a complex number, so you integrate over this modular parameter here. And then you also have a partition function for the closed string, where this z over tau and tau bar is now a trace over the closed string Hilbert space, which of course has left and right movers. So it's a natural generalization. You compute this trace. And then for the closed string, the requirement is that this partition function is modular invariant. Modular invariant under the what is called the modular group of the torus. I don't have the time to explain all this, but what you do is you send tau to a tau plus b c tau plus c plus d, where a, b, c, d are all integers, and they satisfy a, d minus b, c equal 1. Yeah? And you require that the whole thing is invariant under that. Okay? Which gives extra constraints on these modular invariant partition functions. And here, it's slightly different. Here, again, the model, one of the elements here is tau goes to minus 1 over tau. Yeah? This is called also the S transformation, which is part of the modular group. And here you also see, also for the open string, so say the modular group comes up, modular transformations play a role in relating these two different channels, 3-channel and loop channel, to each other. So it's a slightly different story. But again, so to say, the nice mathematics of the modular group, modular forms comes up here. This is also interesting for mathematicians. No? So mathematicians have studied such modular forms for a long time, also in number theory. So it's a very important tool. And also naturally comes up in string theory. Okay, so this I wanted to say. Yeah? The same story with extended supersymmetry. The definition will be the same, but you also have to sum over the spin structures of the fermions. So I don't know whether he did it, but you have Neveu-Schwarz and Raman sectors. Did he that? Different kinds of boundary conditions for the free fermions. And in the partition functions, so under modular transformations, these spin structures are exchanged. So you have to take a sum in order for the whole partition function to be modular invariant. This gives you what is called the GSO projection. So that for space-time supersymmetry, it's known that you have to do a GSO projection, so project the spectrum onto states which are invariant under -1 to the left and right moving fermion number. But even if you don't know this, if you just follow your mathematics and construct a modular invariant partition function, you will find that you have to take this sum over the spin structures, and automatically that you have to do the GSO projection in order for your theory to be modular invariant. Yeah? So it's another way of motivating it. Yeah. Well, I don't think so. Originally, it was just motivated by realizing you have space-time supersymmetry. To project your fermionic string spectrum in such a way that you can get rid of the tachyon. But also, let me see. No, it's okay.
For higher loops, does this lowest loop imply for higher loops?
This is what you learn usually. I haven't seen a proof, but so to say, what people always tell you is if you have consistency of the conformal field theory at tree level, so sphere and one loop, I'm only talking about closed strings now, then you are guaranteed to find consistency also at higher loops. So these are global diffeomorphisms. So you cut your torus, twist it, glue it together, and higher genus surfaces have same sort of Dehn twist. And then you have to show that if you satisfy all these constraints at one loop level, also these other constraints are satisfied automatically. And I think this has been proven rigorously just for the closed string, but for non-oriented surfaces and with boundaries, I think this hasn't really been proven.
And what's the reference for that?
The reference?
Yeah, for the name of the
Who did that?
Yeah.
I would say it's somebody like Dijkgraaf, Verlinde maybe. So in this direction I would look. Not 100% sure. Yep. Okay, so this essentially I did. Okay, so we have already started talking about it, so then we discuss now the extension to the superstring, which means that we are also taking free fermions into account. So I will skip part of my lecture, because I want to explain the Orientifold constructions, at least have the time in the last lecture, so I'll do it slightly shorter than I plan to do it. So some formulas you just have to believe me. Yeah. This one. Okay, so now this is, I think, chapter 3 now. This is boundary states, or the extension of what we just did for the superstring, boundary states for fermions, worldsheet fermions. Okay, so now the situation is different. Now we know that the critical dimension is 10, not anymore 26. D is 10. And we are talking about, if we just looking at the theory on Minkowski space, that we have free bosons and free fermions, where the index runs from 0 to 9. And in light congate, you can get rid of 2 of these fields. And we just extend what we just did naturally to the fermions in taking the square root, roughly speaking. Yeah? So we have, in this case, this was explained, I think we have a Niveau-Schwarz sector where the fermions, they have a mode expansion of this form, psi r c minus r minus 1/2. And here, but I can also do it like this. So in this case, so it's Niveau-Schwarz. So if r runs over the half integers, and it's Ramond if r runs over the integers. So you find different boundary conditions if you take a loop around the origin for these free fermion fields in the 2 cases. Either you get a minus sign, in the other case a plus sign. But since these are fermions, and all what you observe in nature are bosonic fields, you have to take 2 fermions, so you are free to have this extra sign, degree of freedom. And they satisfy a commutation relation, psi r, psi s, equal to ij, delta ij, delta r plus s, 0. Okay, so now the idea is to extend the gluing conditions which we had for the bosonic modes to these fermionic ones. And the right way to do this is to require that psi r, again we have 2 possible signs, plus minus, and now there's sort of the square root of minus 1 here, so here there's a factor of I coming in, eta psi bar minus r for each possible I, what I'll call it j. On the boundary state has to vanish. This didn't understand you? Yeah, this is what I'm just wait a moment. So eta is just a factor. Another factor, another freedom we have is plus minus 1. It's just a number, plus or minus 1. Yeah? So this sign, again, distinguished Neumann from Dirichlet. But in addition, I have this extra sign freedom, which again is related to the spin structure I have. That's different choices for the fermions. Come say, patient. You're too fast. Cannot explain everything in a second. Oops. Okay, so, and I'm sure you believe me that the solution to these gluing conditions is very similar to what we found for the bosonic modes. That again is an exponential of minus now plus I eta, the extra factor, sum over all positive r's, psi minus r, psi bar minus r on the vacuum. Yeah? The meaning becomes clear now when we compute the overlap.
partition, how to put delimiter non-normalism in the position?
This can also be done. This can be done. You have to do this what's called doubling trick. I wanted to circumvent this and just explain the boundary states. Can be done. Yeah. But you have to be very careful that you take all possible signs, extra signs you have into account. That you're not missing a sign freedom you have. Yeah. Okay. So, yeah. So now we compute this overlap. So the partition functions, say in tree channel, and just do it for the Schwarz boundary conditions. Then we have the two possible choices of the sign here. Again, I propagate it to the right-hand side, and I compute the overlap with the same state. Again, I said I will shorten this so I don't explain everything, but hopefully it's clear. So what I get is a new modular invariant partition, a new modular function, which is called θ3 with argument minus or 2il. So what is θ3? I will explain. Do you know what this is? No, it hasn't been explained, no? Okay, so these θ functions with two characteristics a and b, depending on q over eta. This is the definition, is defined as e to the 2 pi I a times b, q to the a square half minus 1 over 24, I think. And then there's a product, n larger equal to 1 minus e to the 2 pi I b q n minus a minus 1 half 1 minus 2 pi I b n plus 1 half. Sorry, n plus a plus minus 1 half. I hope that's correct. And θ3 is by definition this θ function with argument 0, 0. Okay, so if you have 0 here, so these faces are all 1. If here's a 0, so you have n minus 1 half here, and you also have n minus 1 half here. So these are precisely the excitation. Oh, there's a plus sign here. Sorry, there's a plus sign. So these are precisely the partition function, if you want, of a free fermion, taking the Fermi statistics into account. Yeah? M? No, it's N. Here? It's pi IB. Pi IB. The same here. Yeah? So these θ functions, so to say, they are the partition functions for the free fermions, generalizing the 1 over the eta function for the free boson. So this is the partition function of a free fermion, which has, for a equals 0, you have n minus 1 half. So here, effectively, the L0 eigenvalue is half integer. So you have the partition function in the Schwarz sector. Yeah, so this is NS, what we expect here, for the same sign. Okay, so and now if you compute, if you have here the different sign, so if you have now here b plus eta plus minus 1, b eta minus plus 1, so of opposite sign, what you then find is what is called θ4. So you get extra signs, of course, in your partition function. And θ4 is defined as this general theta function with argument 0, 1/2, or it's called characteristic with characteristic 0, 1/2. So what is changing? So b is 1/2. So here there's no change, but here is a change. You get a different sign here. You get a minus sign instead of a plus sign, which means that every fermionic excitations gives you an extra minus sign. Yeah? So this also appears in the GSO projection. If you do the GSO projection and apply -1 to the FL, you just precisely move from θ3 to θ4 on the level of partition functions, because each fermion gets an extra minus sign. Okay. The Raman sector is a bit more intricate, and this is the part I wanted to keep short, because in the Raman sector you have these fermionic zero modes. And so to say, your ground state will be degenerate, because the ground state will be a representation of this zero mode algebra, which is a Clifford algebra, so you get a finite dimensional ground state, and you also have to implement your boundary conditions on these ground states. Okay? So the Raman sector. Okay, so you see that this meaning of these signs here is that you change in the closed string channel the GSO projection, so to say, that you are getting the piece which really, so to say, get the full GSO projected closed string spectrum. Yeah. So the Raman sector is a bit more integrate because you have the zero mode algebra, and first you have to find a representation of the zero mode algebra. So, but what you get then is a degenerate ground state. Maybe this has been explained, I don't know, in Niels' lecture. So you get the same exponential for the boundary state at there, but now your ground state itself, B, or ground state, BR0, is degenerate. Yeah? And when you compute the overlap, you will get the last friend of these states. Again, you can do it B Raman with the same sign. And what you find is what is called θ2. Oops. Over eta, where θ2 is equal to θ 1/2 0. So 1/2 0 means that the phase again is 1, but now this parameter A is 1/2, so you get here integers in the exponent. So your modes are integers now, not half integers. So you are in the Raman sector. And when you have the different sign, you get, so to say, the GSO projection acting on this state. And since the ground state is degenerate, it's actually twofold degenerate for a single complex fermion, and one gets a plus sign, the other one gets a minus sign under the GSO projection, everything cancels. So it's 0. Yeah. Okay, so these are the building blocks. Oh, maybe I need this. For now, building the boundary state of a complete supersymmetric D-brane. B? Without subscript. Here? Yeah, that's missing. Different signs. Yeah, that's okay.
for RR sector initially? Is it?
Say it again.
How are we constructing boundary states for? Are we constructing for any sector, RR sector? Or
Yes, in each sector we can have a different boundary state.
so what about RNS sector?
Hmm?
What about RNS sector?
The
RNS sector.
RNS sector. The overlap between the different two. This vanishes. This vanishes because the ground states are orthogonal to each other. You define them to be orthogonal to each other. RNS vanishes. Good point. RNS vanishes. Now these are different closed string states, so the scalar product between them is 0. Only the scalar product between identical states is non-vanishing. Okay, so if we now collect everything together, so remember, so we're doing the type 2 string now. So we have type 2. Okay, we are doing type 2. There's A and B. Two different kinds. And one has to implement, they are distinguished by how the GSO projection acts on the left moving and right moving Raman sector. So there are two GSO projections. I hope this has been explained, I'm not sure. In his lecture. -1 to the FR over 2. So two independent GSO projection, one in the left movers and one in the right movers. And the distinction is this sign here in the Raman sector. So in S sector they're the same, and in the Raman sector you take up either the same or opposite ones, and this distinguishes type 2A and type 2B. Different ones is type 2A, same ones is type 2B. And moreover, one needs that -1 to the FL, FR on the ground state, which is tachyonic. This is the one we would like to get rid of. This acts as -1 on it. Okay. So now we define the boundary conditions or gluing conditions for a DP-brane. These are now these supersymmetric things. So we have Neumann boundary conditions, a number of directions. These are the ones on the blackboard. DP. And we have this distinguishing sector eta. And this goes from mu from 0 to P. And then we have Dirichlet boundary gluing conditions in the remaining ones. So there's a sign change here. Up to 9, so we have 10 directions. And for the fermions, similarly, we get here plus I eta psi bar minus R so yeah, and Dirichlet and the other ones. And in addition, we have this freedom of sign here, the eta. Maybe I call this M now. This is what I called M before. M. Okay, so we are not ready yet because we have these different sectors and we have to know how to put these different sectors together to get the complete boundary state, which is supposed to be supersymmetric and GSO invariant. Because we're performing a GSO projection. We can write down the solutions to these equations. This I have shown you before, these exponentials, and just multiply them so that in the exponent you actually add all these terms. And we also have to take care of the zero modes, which I don't explain. So that's, and in addition we have for the fermions, so we have this sign, plus minus 1, and we have also the possibility to have Neveu-Schwarz and Ramond sector. So integer or half integer or integer modes. So we have 4 different sectors. No? So the question now is how to add up all these boundary states to give something which is supersymmetric. This is the question, or the problem we have to solve. So let's consider what is easier, which I will explain. The NS sector. So if we act with a GSO projection, on just the boundary states, the pieces here in the NS sector, we get that minus 1 to the FL. Yeah, so look at the solution. Remember there was some exponential, and there was some psi minus r psi bar minus r. So now if you act with the fermion and the sum over r, if you now act with the left or right moving fermion number operator, so you get a minus 1 for each of these things, but only in one. So if the left moving, you get a minus sign from this one, so you change the sign here. Is that clear? The same for the right moving one. Yeah, so if you act with minus 1 to the FL on the boundary state eta in the NS sector, you get the boundary state with the opposite sign here, minus eta. You change this sign here in front, which is the same as changing the sign of eta. And because we would like to act with a minus sign on the tachyon, which is the ground state, get an extra minus sign here. And the same with minus 1 to the FR. Thus, to have something which is invariant, well, we just take the difference of these two boundary states. Yeah? So we take dp ns now is defined as dp eta equals plus 1 minus, this minus sign, dp eta equal minus 1. Because if we add with the GSO projection on that one, we get that guy, and the other way around. So the whole thing is invariant under the GSO projection. This is guaranteed now. However, okay, let's check whether this makes sense, what we get by doing this. If we now compute the overlap of this guy with itself, so we have the overlap of this guy with itself, and this guy with itself, same sign of eta, and then the cross terms. This guy with that guy, and that guy with that guy. This we have already computed. So what we get is C of L for the overlap, dp ns e to the minus 2 pi L h dp ns. So that this thing becomes theta to the 3 to the 4, because now I'm considering all the fermions I have in light cone gauge. I'll do this over eta to the 12 minus theta to the 4, theta 4 to the 4. So let me explain. So the first one here is from the overlap with this guy with itself plus this guy with itself. Let's write the proportional here. Normalization we fix later. this gives you, because I have eight free fermions in light cone gauge, this gives you a factor θ3 to the 4 over eta to the 4. And in addition, we have the 8 bosons in light cone gauge. So we get another factor of 1 over eta to the 8. This explains the 12 here. And this guy comes from the overlap, the cross terms, that with that and that with that. This is the second piece. This we have computed already. This was on the blackboard. Okay, this looks fine. Almost. Not complete. So this is in loop channel. This is in tree channel. So this has the argument 2IL. Let's transform this to the other channel, to the open string channel, where we have a trace. About the what?
The indices, mu runs from 0 to...
Oh, sorry. P. Here's a mistake. And P plus 1, no better? Yeah, sorry, that was my mistake. Okay, so now we transform this amplitude as it stands to the other channel. No? So we get a C of t, and we have to apply, as we learned, a modular transformation, S transformation. On the eta function, we know what it is. Eta is essentially invariant, so we get IT. And now I'm telling you, this now you have to believe me, that under a modular transformation of θ3 is invariant. So θ3 stands as it is, but θ4 is not invariant. Under this modular S transformation, θ4 becomes θ2. So here's a θ2 in the other channel. But this guy has to have the interpretation of a trace over the open string excitations. So we can read off from this partition function now what is the spectrum of this open string theory. And what is it? θ3 is Lewis-Schwarz sector. θ2 is Raman sector. Yeah? So we have θ3 here, that's fine. But what is missing in this channel is the GSO projection. The GSO projection would mean that here's also a minus θ4 to the 4. So that you get rid of the tachyon. θ3 contains the tachyon, but there's nothing to project it out. This term, which does the job, is missing. So we are not ready yet. Yeah, we are not finished. So this thing still is tachyonic. So this D-brane, as it's constructed, is still tachyonic, so it's unstable. It's not a stable, supersymmetric object. It's not what we want. We are not ready yet. We are not ready yet. Yes?
What is the definition of θ2?
Oops.
Ah, okay.
You're welcome. Okay. So there's still something missing. Well, and what is missing, we have just considered the Lewis-Schwarz sector. For the boundary states is the Raman sector, of course. So what is missing is the Raman sector, boundary state. And this is now, fortunately, a little bit intricate story, which I feel I don't have the time to explain in all detail. So what you have to take into account, which I don't do, is really the zero modes. And this is important. And what you then find, if you do this correctly, you can find this computation, for instance, in a paper by Matthias Gaberdil, a number I don't have available, and in the upcoming new edition of our book, this is myself, Lust, and Tyson. Maybe some of you have seen the old version, so there will be a new edition in maybe half a year or so. But this computation will be explained in detail. So the upshot is, if you do everything correctly with the Ramond boundary states, you find that if you act with -1 to the FL, so the left moving GSO projection on that state, that you get the same result as for the Nebo-Schwarz sector, that you exchange the eta and the minus eta terms. But if you use the right moving one, so first of all, you have to extend the GSO projection to the zero mode sector, so there's some work to be done. You find that it's not so easy. There's an extra sign appearing, and this extra sign is -1 p plus 1. Yeah. And this sign tells, now we again construct a boundary state which is invariant under both of these G0 projections in the left and right moving sector. So the first one you can again easily satisfy by taking just the sum of the two boundary states with plus +1, eta equals +1, and eta equal -1. But then the second is not automatically satisfied. Depends on p. However, if you take this one and apply -1 to the FR to this state, you find, of course, that it's -1 p plus 1 dpr. So get this extra sign. And then it follows. So now comes the distinction between type 2A and type 2B. So remember, in type 2B we take the same GSO projection, whereas in type 2A we take the opposite one in the Ramond sector. This is the one we are talking about now. So if in one case you are allowed to have your positive sign, in the other case you have allowed to have negative sign. Yeah. So it follows that this thing is minus FR invariant for if P is odd, the sign is +1, that's fine, the same GSO projection, this is fine for the type 2B string. Superstring. And if P is even, for the type 2A. Superstring. So, GSO invariant boundary states in the Ramond sector are allowed for the type 2B string only if P is odd. This means we have a DP brane where P is odd, so which is actually even dimensional. And so like D1, D3, D5, D7, they exist in type 2B. And the other one, D0, D2, D4, D6, exist in type 2A. This is what we have just pretended to have derived. Of course, I didn't give you the detail, yeah? But it comes out even from this complete CFT consideration. You don't need any space-time solution or solitonic solutions. And this is consistent with what kind of forms you have. No? Remember, in type 2B, you have in the Ramond sector, you have a C0 form, you have a C2 form, and you have a C4 form. And these couples to a one-brane. Sorry, nonsense. This couples to a D-1 brane. Remember, P brane is P plus 1 dimensional. And this is a D1 brane, and this couples to a D3 brane. So all odd numbers. And this is consistent with what we found here. So we have the right forms to couple to these objects, which we found by the CFT analysis. And for type 2A, it's just different. Then you have C1, C3, and you have a D0 brane and the D2 brane. Yeah. Okay, so what is missing now is the complete boundary state. But this is now easily done. We just add the Nemo-Schwarz sector piece and the Raman sector piece we have just computed. And if you then take the overlap, then you find that you get your right G0 projection over there, that the θ4 also comes in. So now if you take the complete boundary state of a dp brane to be the dp and s plus, actually there's an I to get the right factor, dp Raman. If you add these two and compute the overlap, you get θ3 to the 4 minus θ4 to the 4. This is from the NS sector. And from the Raman sector, we get this θ function θ2 and 0. So 0 we don't write. And now you see, if you now do the modular transformation to the other channel, where this should be a trace, and you find that θ3 is invariant. These two are exchanged under modular transformation, so it doesn't change. So it's invariant, the whole thing. So now here we have also our G0 projection in the NS sector. And in fact, one can show there's an identity between θ functions. It's called the Jacobian-Tipper identity, that this thing vanishes. It vanishes because you have the same number of states in the Nemo-Schwarz sector as you have in the Raman sector. And NS sector states, these are space-time bosons, like the gauge field. And these guys, the Raman sector, are space-time fermions. So this is precisely what you expect for a supersymmetric partition function where you have the same number of bosons as fermions. So they cancel in the one-loop diagram. Like the one-loop diagram for supersymmetric theory vanishes because the bosonic and the fermionic modes, they come with different signs and they cancel. And this is the same as here. Okay, so this is our complete boundary state for the for a D-brane in the supersymmetric theory. The partition function vanishes, which doesn't mean that there's nothing. Of course, you have your NS states and you have your Raman states, your space-time bosons and your space-time fermions, and you can read off the degeneracy if you treat these terms individually. Good. Done. So are there any questions? So this finishes what I have to say about boundary states and D-branes. Then I will come to Orientifolds. Excuse me? The partition function as the whole thing vanishes. Vanishes, 0. Because there's first of all, there's a physical argument, but even these are mathematical expressions. If you add them up, they are 0. At each level Q, they are vanishing. This is what is called Jacobi. It's a Jacobi triple identity. It's a mathematical identity. For mathematicians, it's an identity. For us, it's a reflection of space-time supersymmetry. So physicists have an interpretation for this identity. Okay, then
How do we classify in the boundary state formalism of extremal, non-extremal supergravity?
Yes?
How do we classify it in this formalism?
How the difference is? Yeah, I mean, the extremal ones are the BPS states, are the supersymmetric things I have just shown, which have a supersymmetric spectrum. The non-extremal ones, they're non-supersymmetric, so then the partition function wouldn't be 0. Of course, there's I showed you one. If I leave out the Raman sector piece in the boundary state, just the NS sector, I get something, but this is unfortunately unstable. So this is even so non-supersymmetric that it wants to decay into something else, because there's a tachyon. Yeah? Good question. Good. And maybe I should mention, while I erase the blackboard, there are also, but one can also construct boundary states which are non-supersymmetric, yeah, but don't have tachyons. And they are called stable non-BPS boundary states, or branes. And they also play a very important role in string theory and show up. And this is now for experts. The classification of these things has something to do with K-theory. Okay? So if you find certain torsion classes in your K-theory, then these are related to these stable but non-BPS, non-supersymmetric boundary states. But it's always, I find it always quite intriguing. If you just follow your rules of two-dimensional conformal field theory, you get some result, and then if you rethink what you actually have done from the space-time point of view, that you have computed something which has a nice geometric interpretation. Like in this case, that K-theory actually, what you just follow you just look at whether your partition function has a tachyon, but this tells you something about some C2 torsion classes in the K-theory. I mean, this is non-trivial, yeah? And this is the nice thing, interplay between always worldsheet consistency and space-time consistency of string theory. There are more other examples where, in principle, so geometrically, for instance, massless spectra are computed by certain cohomology classes on Calabi-Yau spaces, for instance. Well, if you don't know how to compute this, but if you have a CFT description of this model available, well, you just do your CFT computation and just count massless states, and you implicitly compute these cohomology classes. Yeah. Another example is mirror symmetry, where a completely trivial operation in the CFT, which tells you that if you just flip a certain sign, you get an identical conformal field theory. But then if you rethink what this means from the space-time point of view, you mean you have really exchanged your, for instance, Calabi-Yau compactification by going to a Calabi-Yau which has the opposite Hodge numbers, which is a completely different geometry. And in fact, mirror symmetry was detected by string theorists just analyzing these conformal field theories and finding, well, that they show this mirror symmetry and that it's completely trivial to have this extra sign flip, which has a deep mathematical meaning and a lot of implications. Okay, this will dry out. Okay, so if there are no further questions, then I have half an hour. I will start to tell you a bit more, something new, on what is called Orientifolds. D-branes and Orientifolds are intimately related. So if we are in a compact space, maybe I'm motivated. So if I say I compactify my 10-dimensional space-time, I might have the idea, so here's my 4-dimensional flat space, and I might have the idea, well, I just put a brane here. Maybe we're on a sort of a brane world scenario, right? So we have a brane here, a D3 brane, which wraps this space, which might also be higher dimensional, and then in addition wraps some internal cycles of our internal manifold. We might have the idea, well, I just built such a model. That's a nice thing. But if this space is compact, it turns out you're not allowed to do that. Because this D-brane, so it carries a tension, this we have seen, because it couples to the graviton, it has a tension, a mass density, but it also couples to these Ramond-Ramond forms. Ramond-Ramond forms are like gauge fields. Yeah, so they also carry a charge under a certain Ramond-Ramond form. And now, maybe you know from electrodynamics, you are not allowed to put a single electron on a compact space. There are flux lines. It violates Gauss' law. The flux lines have to go somewhere. So there must be, here's a D3 brane, there must be an anti-D3 brane somewhere else so that the flux lines also have a sink. This is Gauss' law, applied on a compact space. So there's a problem with putting or placing D-branes just on these compact spaces. So we can't build brane world models in such a simple way. I mean, if this brane doesn't cover our entire 4-dimensional space, if it just covers, say, a 2-dimensional slice, which is not realistic. No? But this wouldn't be a problem, because then the flux, so to say, because this space is infinite, in this direction it can escape to infinity. But it's not allowed to put it on a compact space with only finite transversal directions. So there's a problem. So we need objects. So one option would be to take a anti-D3 brane. Then it has the opposite Amora-Moore charge, but it has the same tension. This is fine. So we just have extra tension on this space, but it breaks supersymmetry. So it's not so really nice, right? So you break supersymmetry. And generating a cosmological constant in your space. And usually these things are not stable, no? So they will try to attract each other, and then poof, no? They will decay. So we need other things. We need objects to make this correct. We need objects which have the negative charge, but also negative tension. So here also a minus sign. Then we could have these extra objects, call it O3, on the compact space, and they would precisely cancel both the charge and the tension of the D3 branes. Yeah? Then we have a chance to build something like compact brane world model.
And then
Then
it's supersymmetric.
supersymmetry, that is meant to be C, has a chance to be preserved. And it's indeed the case. Sorry?
You said that you had a chance to preserve.
To preserve supersymmetry?
How do you see this?
Not from here, but at least because you have a positive tension here, you have a positive cosmological constant. This means that you have broken supersymmetry. Here, you don't have, so you have a chance to preserve supersymmetry. This is the logic. Yeah? And I already denoted them as O3. So these objects with this property, these are what is called Orientifold planes. And we'll see that they can really appear, and they do show up in string theory. And they are also related to the classification even of 10-dimensional superstring theories. Remember, there's type 2A. There are two kinds, A and B. Then there's heterotic, which I guess hasn't been explained. Is that correct? Or was it treated? A little bit. Okay, there's heterotic. There are two incarnations here, SO32 and EA cross E8 as gauge symmetries. So they're anomalous. The pure gravity theory is anomalous, so you need extra gauge degrees to cancel the anomalies. And then there's this strange type 1 string. Was this mentioned? Type 1 was also mentioned, but was it explained? Okay. So this is the first example of an Orientifold. So the prime example. And this is what I will try to explain. This is the idea. This is, so to say, the project for the next for the rest of the lecture. And this has also gauge group SO32. If you have a positive charge, positive charge is not allowed, because then you have this problem with the charge on the compact space. This must be. This could be positive and negative. Here's no for tension. There's no Gauss law. Okay, so this is the idea behind that, and this is why we are now discussing these Orientifolds, and we will see that the formalism is very, very similar to the D-brane formalism. I just put some extra minus signs somewhere. Yeah? But the construction is completely different, because it involves, chapter 4, so unoriented worldsheets. What does that mean? So far I was talking about the annulus for an open string as a one loop diagram, or I was talking even about the disk, disk, or I was talking about the torus or sphere or torus. They are all oriented. But they are also non-oriented surfaces, like a Möbius strip, which I can't draw. Well, I just draw it in my way. So this is a Möbius strip. Yeah. Or an RP2. This I can draw, I think. So I take the S2 and identify opposite points. Then I get something like this, half semisphere. But on this circle, I also have to identify opposite points. So this is usually denoted by such a symbol, which is called a cross cap. This means that I identify on this circle opposite points. So this is RP2. Okay, so
So Orientifolds also has an interpretation in terms of open strings.
wait a moment. You're fine. Not really. You are too fast. Wait a moment. Okay, so how can we get these non-oriented strings in string theory? I mean, they're not necessarily there. So what I have to do is I have to have the string non-oriented. So first of all, a string, let's draw both a closed string is oriented. I can give it an orientation, left moving and right moving modes, or the other way. The same for an open string, I can give it an orientation. So if I want to have non-oriented things, what I can do is I have to identify different orientations. So if I do something like on the worldsheet, sigma tau goes to, let's do it for the open string, pi minus sigma tau. So I change, by this operation, I change the orientation of the open string. And if I write it 2 pi, I change the orientation of a closed string. So what I can do, and this operation is called omega, so it's omega, so it's called worldsheet parity transformation. Worldsheet parity, so it changes the orientation. And this is now a general concept of string theory. If I have a string theory and I have designed it such that it has a certain symmetry, either from the worldsheet or even from space-time point of view, to the space symmetric, then I can gauge the symmetry. I can identify configurations which are related by the action of the symmetry. It's called the gauging of the symmetry. Yeah? The same I could do for instance, if I have, if I compactify on a torus, like this one, and I see that there is a certain C3 rotational symmetry, I could take the quotient. I could consider something like T2 over Z3 and try to compactify my string theory on such a space. This is usually called an orbifold. Yeah. This is space-time symmetry. And now here I have a worldsheet symmetry. So I require that my string theory is such that it has this symmetry, and if it has this symmetry, I can gauge it. So I can take the quotient. So I can take, for instance, type 2b, which is left-right symmetric because I have the same GSO projection in the left and the right moving sector. The spectrum is completely left-right symmetric. Yeah? So I can, from this theory, I can take the quotient by omega, by identifying configurations which are related by omega. And yeah, this is type 1. Yeah? So what we will do now is we will consider such quotients by omega. And this is called an Orientifold. Yeah. So these are orbifolds, and if it involves omega, it's called an Orientifold. There is a history. I don't know whether I should tell it because I'm recorded. So this term was introduced, I think, in 1995. I think it was by Witten, actually, and Waffer. When it's superstring revolution, so the revelation of dualities and so on took place. But in fact, as a matter of fact, these kind of models, except for the type 1 string, even generalizations of taking quotients which combine, for instance, such orbifold operations with the worldsheet parity transformation, were already be done, I think, from the late 80s on by an Italian group, Sagnotti and Bianchi. So they reinvented a lot of things these people have done, actually, and gave it a new name. And the fun thing is that you will see that in these Orientifolds, and also in order to, you can't, in the same way as you can't have a single D-brane on the space, you can't have a single Orientifold plane on the space, so you need to put in both D-branes and Orientifold planes to cancel these charges. And these people have done this all the time using pure CFT, algebraic CFT methods. And this is one of the examples where they didn't realize that they are doing something very interesting from the space-time point of view. Yeah? Because they were treating, on the CFT level, all the time, what now are called D-branes, which officially have been invented in 1995. You see the point? So they have done this, all these things before, but they didn't realize that their Gen pattern factors, they are really related to D-branes. For instance, they found gauge groups. So this gauge symmetry is SO32. They found gauge groups like U16 cross U16 in their constructions. The large gauge group has the rank twice of the 10-dimensional theory. So this cannot be a simple compactification of this 10-dimensional theory. Where should all the gauge degrees of freedom should come from? Well, the solution is, well, here are D9 branes. These are these guys. But here are also D5 branes. This is what we know today. But they didn't know. You know, you see? So D-branes were hidden in the literature, but not realized to be present. Okay, so now how do we treat these things? Well, let's look what happens to the spectrum again when we apply this omega worldsheet parity transformation. And but we can keep track of that by looking at the partition function, now on the torus. So on the torus, I mentioned already that I write down a partition function taking care of all states in my closed string theory. So usually I choose the same central charge, otherwise it isn't left-right symmetric anyway. Yeah, so this is over the closed string Hilbert space, left and right combined. And if I know this thing is symmetric, I have an action of omega on my space of states, so I can do the projection. And this is done by introducing a projection operator. Yeah, so I introduce here in the trace 1 plus omega over 2. So this is a very simple action. Usually you have a state ij, left, right moving. Well, under omega, you exchanged left and right. Well, I haven't said this. So if you have tau minus tau plus sigma, so if you do this changing of the orientation, you exchange these two things. So you get sigma to minus sigma. So if you have here sigma from here measured on minus sigma, this is the worldsheet parity in the closed string, which exchanges left and right. Yeah, so yeah, U and V, so they are exchanged. So the only thing you're doing is you're exchanging left and right, so you map this to I, Ji. So you're only keeping, so the states which are invariant are only those which are left-right symmetric. And using this action, so you can introduce here the projection operator. This is the projection operator, no? 1 plus, because the square of this is 1. And so define a new theory. And then you can write this as 1/2. This is from the 1 of the former torus partition function. Yeah, call this torus. Plus 1/2 of the trace of omega q to the L0 minus c over 24 q bar L0 minus c over 24. And this is what you people call, it's got the Klein bottle, C Klein bottle. Why is it called that? So you have your closed string. So you start with your torus. This is a torus diagram. You identify opposite sides. This gives you a torus. And as we have seen, this operator, if I am in Hamiltonian formalism, this is what I am in, this operator here tells you the twist you are doing if you go in the time direction. No? So if you go in this direction, you see that you change the orientation. So if you are here, you change the orientation. So we come up with a different orientation here. And this is a Klein bottle. Yeah, so you do a torus, you do an annulus, and then you glue together with a different orientation. So there are drawings. In the literature, you can find strange drawings of these things. I can't do this. Yeah? This is simply to draw. Okay, so and because we are keeping only states, so if we now take the trace, so I have a state here, I apply omega, exchange left and right, and then I match it again with the original state. Clearly, only states which are completely left-right symmetric contribute to this object here. Yeah, so there can only be states which have the same L0 and the same C. So this simplifies this expression. So I'm only interested now in this guy. So this becomes the trace of omega and e to the minus 2 pi t, where, let's see whether I did this correct. So tau is tau 1 plus I tau 2, and this tau 2 I call t. This becomes 2 pi t L0 plus L0 bar minus c over 12. Yeah? And this is called the Klein bottle amplitude. Yeah, sorry on the blackboard. Okay. So, you see what I wanted to say? Yeah, so this expression, remember the formula. Now I do just an analogy. Remember the formula for the annulus diagram. And here 1 minus 2 pi t L0 for the open string now. And here's closed. Yeah. So it looks very similar to this expression except for the introduction of this omega here. And here we saw that we can write this, the annulus, have a different interpretation also as a closed string exchange between two boundaries. Question: can we give the same interpretation, a similar interpretation also to this amplitude? So can we write the Klein bottle as something like this? That's not so obvious, but it's possible. And here are the manipulations I have to do. Let me see whether I get this correct. So I start with the Klein bottle. Okay, and now I cut it along this line here in the middle, and I shift this upwards. So what happens? More space. So this half I shift upwards. So I do the drawing. Here, here, here. Here. Okay, so this point, let's look at this point, was identified with that point. Right? So, see, this point, for instance, is identified with that point. And since I cut it here, let's see, what am I doing? All right, okay, these points are interesting. So this point is identified with that point, for instance. So this means this point is identified with that point. So these points are identified. So now I flip this over. Can flip this over and can glue this together here because these are the same point anyway. So I flip this over. So here I'm fine. This is together. So this line, see, was identified with that line, but now I flipped it over. So look at this point. It was here. Now I flip it over. So this is identified with that point. So here I have now this identification along this line. This looks good. This looks already like this tube. Yeah. But now we have to look at the boundaries here. You see here, this point, for instance, was identified with that point. Now it's flipped over. So here I have just this shift by 1/2. So this is with that, this with that, this with that. So I identify, if I now draw it in this form, so I identify these lines. And here on these boundaries, I identify opposite points. So this is the diagram I have to draw. So it looks like a tube with 2 cross caps, each on one side. Yeah, so we get a non-oriented diagram. This is obviously here, but here is also obvious. So it's what we expect. We get something non-oriented. And we have just written the Klein bottle in a different way. But here, we can now try. This now makes sense. Well, maybe there exists something like the analogous thing of a boundary state for this cross cap, which emits closed strings, going to the other cross cap and being reabsorbed again. Yeah, so we expect that there, or we have a chance that there is something analogous to a boundary state which allows us to compute this diagram again in both ways, either as a trace over the closed string now with the omega insertion, or as the overlap of 2 cross-gap states with this propagator in between. Yeah? And these states here, these are called cross-cap states. And they are the analogous thing as a boundary state for D-branes. I think now is a good time to stop. So maybe one thing that this I will introduce next time, these cross-cap states. They're very similar to the boundary states. But let me mention now, the final thing is the relation between L and T. It's a bit more integrate here. I hope I get this right. So let's start here. So this is a closed string. It has length 2 pi. I'm looking in this channel. And this is 2 pi t. Okay, and then let me see. Okay, after this 2 flips, this becomes pi, and this is now 4 pt, this length. Yeah, I cut it, so I get just pi here and 2 pi t here. Okay, now I want to have the closed string interpretation. So this is a closed string, so this is 2 pi, and this is again 2 pi L. And the ratio has to be the same, the modular parameter. So 4 pi t over pi is 4t, has to be equal to 2 pi over this, 1 over L. So the only difference to the, well, there's one difference to the annulus, that here L and T are related in this way. L is equal to 1 over 4t instead of 2t, because it's a closed string. This we have to keep in mind. Okay, so here I will continue next time, and next time, I mean in a few hours actually, I will write down the cross-cap states, then we compute overlaps, and then we can redo the type 1 string construction. Okay, bye.